Hello everyone. So in this video, we are going to see this particular question that is related to power system, you can say, or to some extent it is also related to synchronous generator. Like why fault is a high frequency phenomena. So to understand this particular question, I have to take an example of synchronous generator. Let's let's I have synchronous generator with me, and it has synchronous reactance, and it is directly connected to infinite busbar. Okay, and let's say there is a point here, and I will take this point as a faulty point. Okay, so but before that I have to mention some points like I hope you know like what is the swing equation of synchronous generator. It is nothing but m d2 delta by dt square pm minus pe. The pm, this is the mechanical power that is coming from the prime mover, and pe, that is the electrical power that is coming from the terminal of the synchronous generator, you can say. And this m is nothing but it is also called inertia constant, and m is simply gh by pi f if I am taking delta is in it in radian. Okay, so this is my m. It is the inertia constant. H is also inertia constant, but the units are different. Okay, and you have this particular equations. This is called a swing equation. So you need to know this particular equation, and also you need to know the one more equation, that is something called the relative. You can say relative velocity. That relative velocity we call it as d delta by dt omega minus omega s. Okay, this is the relative velocity, you can say, and this omega s is the frequency that is that of infinite bus bar. That's unit is in radian, electrical radian per second. That is electrical radian per second. Okay, so this is the relative velocity, you can say. So and this omega is the uh, rotor speed in electrical radian per second, and this d delta by dt, it is also the electrical radian per second. Like, so the unit must be same for all these three quantities. So this is the electrical radian per second. So these two equations are required to analyze the this particular question, why fault is a high frequency phenomena. And this particular term d2 delta by dt squared, this is we called like acceleration, rotor accelerations. Okay, now let's say you have a fault at the terminal of synchronous generator, and the terminal voltage, let's say you had vt here, and now after fault the vt, like this terminal voltage is going to zero. Okay, the terminal voltage of this, you can say, synchronous generator is simply going to zero, and as the terminal voltage is going to zero, and let's say you have the initially you had this ef at an angle delta. So what will happen the moment as we know, the active power flow is nothing but EF Vt by Xs sine delta. It is the electrical power. The moment you have this Vt 0, this Pe will simply become 0. Okay. Now, from the swing equation, you can write m d2 delta by dt square is equals to Pm minus Pe. This term is simply vanished to 0. You have Pm. Okay. So, if you write d2 delta by dt square Pm minus m. Okay, now calculate the d delta by dt, or the relative velocity, you can say. So the relative velocity, we can call it as a omega r also. Either we can call omega r or we can call d delta by dt. So if we just separate it out, this d by dt term, d delta by dt Pm by m. Okay, now come here, d of d delta by dt Pm by m dt, take integration. Okay, and at t equal to 0, let's say that fault occurred at t equal to 0, so here the lower limit will be simply 0, and I want to know the what is dy dt at any time t, and at 0 time the relative velocity was 0, and at t time the relative velocity is d delta by dt. So if you solve this particular equation, you will get d delta by dt is equals to pm by m t. Okay, so this is I'm calling equation number 3. Now you have this relative velocity. You can see from this equations. Let's say there is a fault at t equal to 0 second, and as the time is progressing, you can say this d delta by dt, or the relative velocity, is simply increasing. So let me take one more slide. So d delta by dt is equals to pm by mt, and also d delta by dt is equals to omega minus omega s. This particular thing is constant, the synchronous speed of the grid frequency. You can say I can write here pm by mt is equals to omega minus omega s, and omega s plus pm by m t is equals to omega, and omega is equals to, I can write omega, just simply I'm just rewriting it, pm. This particular equations, if you see, this particular equation depends on the time. If time is increasing, the relative velocity is also increasing. The relative velocity is also increasing, and the rotor positions, or you can say the rotor speed. If I write this particular equation in terms of in hertz, like this omega is nothing but 2 pi f. Okay, so just divide it. So you'll get f is equals to omega s, like omega s by 2 pi. So it will be fs, the supply frequency or the grid frequency, you can say, by 1 by 2 pi pm by mt. So you have this now, this the generator frequency is simply increasing, and it depends on the time. And you can see here, because of the fault, you are getting the response from the generator, and that response is basically increasing the frequency of the system. So that's why the fault is a high frequency phenomena in either power system, you can say, or in synchronous generator. It is applicable to both, because you cannot separate it out these things, because power system is connected with the synchronous generators and all. So if there is any fault, then the output frequency of the generator will simply keep on increasing. Okay, and that's why, like, there is a certain limits and all. You have the concept of critical clearing time, critical clearing angle, all these things comes into picture to restrict this high frequency things and all. Okay, or else the system will go unstable region. I hope this particular thing is clear to you. If you have still any doubt, you can ask me in the comment section. Thank you.